Hello, everybody. Welcome back to another strengths materials video. This one is on trusses. We're looking at the joint method once again. It's going to be super quick and easy with a lot of good visuals just to see where all the forces are coming from in a problem uh, like this. And you could apply this to any truss problem that you have. The only thing that you need to remember from previous videos, if you want to click the link at the top, you can get a full breakdown of how this method works. You need to understand the convention, and we're going to go through that when we get into isolating these joints. Don't worry about zero forces for now. I don't want to overcomplicate things in this video. Let's just think about how to use the joint method to solve a problem like this. Pretty much it's asking us just to figure out what each force is in each member. Tell them, whoever's asking, if it's in tension or compression, and it gives us the external forces which are being applied at joint F and joint E, which are 10 kilonewtons and 15 respectively. Now, the only way to start a problem like this, obviously, is to solve for our reactions. And in order to do this, we know we need to take a moment about one of these supports. Doesn't really matter which one. Let's say I wanted to start at joint G and take the moment about that point. So we can say for equilibrium of moment, everything has to equal 0. That is our sign convention, negative in the clockwise direction. We're going to have the following forces. Sorry about the voice crack there. We have AX, which is in the counterclockwise direction, which means it's going to be positive, and that's 4 meters away from G. So we have AX times 4. Next, we're going to P1, which is equal to 10. And with respect to this support, we are taking our arm about this direction here from G to B, pretty much. So that's going to be about 2 meters there. And this is going counterclockwise, meaning, or that's going clockwise. Sorry about that, guys. First video, it's going to be a rough one. So we got 10 for P1, that's 2 meters away. And then similarly, we have the P2, negative 15, and then we have 2 plus 4, that's going to be 6. Solving for that, you have AX, which is equal to 27.5 kilonewtons. What's up next? We have to take the summation of forces. So we have AX. We took the summation of forces now. We can actually solve for what GX is. So if we took summation of forces of X equals to 0, we're going to have it equal to negative GX and then plus 27.5. I don't see any other X components yet. So we're going to have GX is equal to 27.5 kilonewtons. The sign is positive, meaning that it is drawn in the right way on the drawing. And lastly, we got to solve for that sneaky AY here. And that's simply going to be using the equilibrium of Y equation. So we have AY first, and we have negative 10 and negative 15. So negative 10, negative 15. Solving for that, you have AY is equal to 25 kilonewtons. Now, what are we going to do? We have the reactions. What can we start with? My mind is telling me to jump to A first because we have 2 known forces already acting inside of this joint here. So let's go ahead and isolate this and see what's happening inside of the truss. Alrighty, so now we have the A joint, which is isolated so that we can solve for the internal forces. We have 2 unknowns for FAB, or FAF, sorry, and FAB. And the way I go about figuring out what to do is looking at what type of unknowns I have. So since this is a diagonal force, we're going to have component breakdowns for the Y component and the X component. And then for FAF, we have a sole X component, meaning that for this joint, we have 2 unknown X values and only 1 unknown Y, meaning that we can go ahead and figure out what that Y component is for FAB. So let's go ahead and figure out what that is. So we take the summation of forces at Y is equal to 0, and we simply start solving. So we have the reaction that we just solved for, which is 25, and then we have the negative Y component for FAB because I'm assuming that this is in compression. So I have negative, I'm taking FAB, and the component to make this Y is going to be 4 over 20. Where did I get this root 20 from? This root 20 is simply from A squared plus b squared is equal to c squared. We know a and b is 2 meters and 4 meters respectively. You bring the root over and you solve for it, you're going to be left with root 20. So that's how I'm getting this triangle in order to figure out what those components are. So simply solving this, we are left with FAB, which is equal to 28. Sorry, 28 kilonewtons. And this is a positive sign. And I've drawn FAB in compression because it's pushing the joint, meaning that this is a compressive internal force. And then similarly, we go ahead and we solve for the x components. So we have what? We have FAF, which is still unknown, but now we have FAB solved for, so we can go ahead and figure out what the remaining unknown is. So our x components are the reaction at x, 27.5. We have FAF, obviously. This is negative because it's going to the left. And then we've drawn this as a compressive force going downwards diagonally like this, meaning that it's going to produce a negative component in the x direction. So this is going to be negative FAB. We know what this value is. This is going to be 28. And the component of this is going to be 2 over root 20. 2 over root 20. Solving for FAF, you will be left with a value of 15 kilonewtons. Once again, we are getting a positive sign. This is drawn in compression because it's pushing the joint, and this is a compressive internal force. Now, which joint can we proceed to next? Well, we can go to G. We could try B, but I think it makes more sense to just start with G and see what happens there. Okay, so I think you can see now why I wanted to proceed with just going to joint G, because it's super simple. We have GX, which is acting in one direction, meaning that the internal reaction being produced inside of the member, or the internal force, FGB, is going to be the opposite of that. So FGB is going to be 27.5 kilonewtons, 27.5 kilonewtons. This is pulling the joint, meaning that this is going to be a tensile force on the internal side. So this is a tensile member here. And next we can proceed to, I'm thinking, joint B, because we have FAB and we have FGB, meaning that we have two forces that we know, which will help us solve for these other unknowns here. Alrighty, looking at joint B, we got another pretty simple one. So I didn't want to break it down too much in this drawing. I'll do it for joint F, but this one's super simple because we already know what's going on with FAB. We have the component breakdown that we can figure out from this special triangle that we've drawn on here. We have FGB, which is one single component in the x direction, and we can easily solve for these other two unknowns based on what we did in that previous problem. So we only have one unknown y and one unknown x, so this should be super simple. If we look at either of these, we should be able to figure out what we're working with. So if we started with f at x, let's say, and we are going to be looking at the internal forces, so we have a negative 27.5, which is being created by this FGB value. We have this FAB, and if we're thinking about the x component being created, that is going to be going to the right, which means that it's going to be positive. FAB we solved as 28 in our previous steps, and the x component for that is going to be 2, which is this x dimension for the truss, over root 20. 2 over root 20. And the last component is going to be FBC. And then solving for FBC, you can bring it over and solve for the value of 15, once again, kilonewtons. Once again, the sign is positive, meaning that we have drawn it in the correct orientation. It is pulling at joint B, meaning that this is a tensile force. And we can do the same thing for Fy. Super simple stuff, guys. Solving for this, we have the unknown y, which is negative, as we've drawn it in our joint breakdown here. And we have the positive value of FAB, because this diagonal is producing a positive y component here. We already solved for it, which is 28. And the y component, we're taking the 4 this time instead of the 2. So 4 over root 20. Those are your only two y components in this problem, meaning that we just bring the FBF over. We solve for it to equal 25 kilonewtons. And we're using the exact same logic here. It's pulling the joint, meaning that this is also in tension. And we can add this to our drawing and then proceed to the next easiest joint, which will be joint F. But let's see what this looks like inside of a more detailed drawing. Alrighty, so we plugged in the other forces that we got from joint B. Now we're looking at joint F. We have it all isolated, nice and pretty for us. So we have a very similar situation that we had at joint A, except now we have a couple more forces that we need to work with, and we have the very similar configuration of unknowns, which is the FFC and FFE. FFE is a sole X component. FFC has an X and a Y. What does that mean? That means we need to start with the summation of forces at Y in order to figure out that sole unknown. And when we do this, the equation is going to look like this. We have the external force. Do not forget about these when you're solving these problems. They tend to get forgotten a lot of the time. So you have a negative 10 because this is downwards based on our convention. The FFB, which is plus 25, and the Y component for FFC, the way we've drawn this, we're going to have a negative sign because we're going downwards based on this drawing. So we have negative FFC, and that component is going to be 1 over root 2. Why is that? You have 1 as your height, and then your hypotenuse is root 2. FFC being solved for is going to be 21.2 kilonewtons. Once again, positive. It's been drawn correctly. It's pushing the joint, meaning that this is in compression. That's probably the main takeaway for these types of videos. Just lock in your convention. You'll be super fine. Try not to get too caught up in the sign convention that you get in the end. Just see what you've drawn and try to work out logically what's happening after you've redrawn it if you need to, and figure out if it's pushing or pulling the joint. I think that's the best way to go about doing it. Next, we have to go ahead and do our fx component, which is going to be this FFE. So we have 0. We have FAF, which we solved so early in this problem. Let's just write the value for FAF. What was that? I believe it was, oh, it's right there. I didn't realize I wrote it here. So we have 15. That's positive, going to the right. We have the positive FFE, which is also going to the right. And FFC is actually going to be going to the left. So we have to make this negative. FFC, this was solved for just above 21.2. And once again, you're taking the x component this time. So we have 1 over root 2. It's the same either way, but just for the sake of the equation, solving for FFE, you're left with a value of, surprisingly, 0. You get a value of 0 here. And this is going to make life so much easier for the remaining parts of this problem, and you're going to see just why that is in these upcoming joints. So let's go ahead and move over to our next joint. We're going to be looking at joint C. Alrighty, so hopping into our next joint here, following the flow of the known forces in our problem, we have joint C, meaning that there is 2 unknowns here that we still need to deal with, and this is once again super similar to what we've been doing. We have one unknown x component, which is being produced by this FCD force, but 2 y values that are still unknown, 100% of FCE, and then the component of FCD. So what does that mean? Since we only have one unknown x, we can go ahead and use the equilibrium of forces at x equals to 0 and start solving as we normally would. Get FBC, which is 15 kilonewtons, but that's negative, don't forget it. It's going to the left. And then the way we've drawn FFC, actually, we know about this now. This is in compression, meaning that the x component is actually going to be going to the right. So we have to make this positive. Let me just make this a little bit clearer for you guys. So that's going to be negative. We have positive 21.2 for FFC. Once again, taking that x component, which is going to be 1 over root 2. But then you have to consider also FCD, which is drawn as positive as well. So we have positive FCD. And a very similar thing that we did previously with this triangle as well, except now we have 2 over root 20. But you're going to realize very quickly that none of this is really going to matter because when you actually solve for FCD, this is going to equal 15. Negative 15 plus 15, that's going to give you 0. Meaning that FCD is a zero force member, surprisingly. You wouldn't instinctively think that, which is why I told you to kind of neglect the zero force member rule kind of at the start. I just wanted this to be strictly focused on method of joints. But anyways, the last thing we need to do is figure out what this FCE is. But now we know that this is 0. So the only other y component is being produced by this FFC, meaning that if we took summation of forces of y equals 0, we have FFC. Actually, let's plug in the value once again. Sorry, I keep writing down the variable. We have 21.2, the y component's 1 over root 2, and we have negative FCE. FCE is going to be equal to 15 kilonewtons. And we've drawn it the right way because this is positive, meaning that this is a tensile value. So that means FCE here is going to be 15. And if we think about this here, this D joint, if we actually went ahead and solved for it, this is going to end up being 0. So I don't want to go ahead and like waste everybody's time. But yeah, that's pretty much the end of this problem. That's everything solved for. If you want to be super accurate with how this should end, you're going to have this looking something like this for FCE. So yeah, hope this helped to understand method of joints and the visuals. And yeah, thanks for watching.